Okay, I think I would just start then slowly. So I would like to welcome you. My name is Irina Heinzig. I'm the technical committee chair of REACT, which is one of the committee which is dealing with climate change and sustainable development goals. And I'm very, very happy today to have today as a webinar, to announce a webinar about EORE for Wildfire, which is given by Yifang Ban. She's the professor and director of Division of Geoinformatics of the KTH Royal Institute of Technology in Sweden. And I'm very happy that she will give a presentation about this very important topic today that is really strongly related to the climate change and also sustainable development goals. And with this, I would like to give my words to Yifang Ban.
Thank you very much, Irina, for the invitation and for the introduction. Good morning, good afternoon, good evening, everyone. I would like to present our ongoing research on how to use Earth observation, multi-sensor data, and deep learning for wildfire detection and monitoring in the near real time. So this is representing my team within the EOAI for Global Change project. The project is funded by Digital Futures and the Swedish Environmental Research, as well as ESA. So as you know, we're facing climate crisis from melting glacier to melting sea ice, drought, flooding, and wildfires. In recent years, wildfires have increased in frequency, intensity, and duration. And you've seen the news of the recent wildfires in Los Angeles. Not only nature areas were burned and, homes and infrastructure were affected and also caused a lot of pollution and CO2 emissions. So wildfire has devastating economic, environmental, and human impacts. So in 2022, the UN has initiated this early warning for all initiative in terms of implementation of climate adaptation. There are 4 different pillars. So one of the pillars is really directly related to Earth observation. So Earth observation can play a significant role in early warning for all. So since we have, since 1972, many Earth observation satellites have been launched, providing petabytes of data for environmental change monitoring, specifically for early detection of wildfires and monitor the fires in near real time. So specifically, I want to show, the both radar and optical data, Sentinel-1, Sentinel-2, launched by ESA. They have global monitoring capacity at, every few days, 5-6 days. Global coverage, if you're up north, is 2 to 3 days. So these are really important data sources for as a source for wildfire monitoring. So in terms of, we're in the era of Earth observation big data. So partly thanks to the fast growth of satellite technology. Another part is related to national, international space agencies. They're moving to launch more satellites, as well as private innovative companies. So you have heard quite many of them. So here I just want to show the ESA Sentinel fleets. I think ESA's, the satellite fleets are the largest globally as a space agency. So you see the SAR optical data capture quite good resolution of cities of Stockholm. And then we have Planet on the optical side, Worldview, and Capella Space, ISI on the SAR side. And the aim, they have ambition of daily or sub-daily monitoring. I mean, Planet has already achieved daily monitoring. So there are a lot of opportunities. So suddenly we have a lot of satellites orbiting Earth that can provide near real-time monitoring. So what are the opportunities? So I already wrote here about near real-time, including wildfires monitoring. And we have dense time series for analysis of global environmental changes. And, in terms of wildfire, not only monitoring and also environmental impact. And then new possibilities for operational reliable services. So can we provide daily or, sub-daily wildfire services in operational sense? And what are the challenges? We have a lot of data. We definitely need innovative computing infrastructure to handle, store, and process those data. We need new methodologies and algorithms to extract valuable information in specifically active fires and burned areas where the fire front was progression, and how to integrate maybe other type of data into EO analysis. Social media, let's say people say, oh, here I saw smoke, there's a fire, then we can start the monitoring. So crowdsourced data, ground-based sensors. So in terms of cloud processing platforms, and I'm sure some of you are already using AWS, Google Earth Engine, etc. In terms of ESA, we have the DIAS. So often, we're in the big data era. It turns out to be more efficient to move the research questions to the data than moving the data. So I think this is the idea. We bring our algorithms to the data. So in terms of wildfire monitoring, we have two aspects. One is to detect active fires, where the fires are active. So in terms of active fire detections, we need really high temporal resolution. Of course, high spatial resolution are also welcome. So in this, we have two groups of sensors, geostationary, 36 kilometers above the Earth, and they can capture maybe every 15 minutes. We have GOES, Meteosat, Fengyun, etc. So there are different weather satellite series. But the resolution is quite low. It's 2 to 3 kilometers resolution. So you need fire sufficiently big in order to be detected. On the other hand, we have the polar orbiting satellites, the coarse resolution, Sphere, Sentinel-3. They have resolution range from 250 meters to 750 meters. This is twice daily, so you have day and night. And Canadian Canadian Wildfire set, to be built and launched also will be part of this series of satellites, dawn and dusk monitoring. So this can also provide, more reliable information because it's a sub-kilometer, then smaller fires can be detected. So in terms of temporal resolution, just to compare, Sentinel is every 5-6 days, and then you have GOES or geostationary. They monitor every 15 minutes continuously. Then you have the sub-daily of the other sensors. So here just showing the animation, how active fires can be readily viewed and detected using this satellite data. And those were GOES, and here are the VIIRs. Then using the mid-infrared, you can see hot spots on the imagery. And this is the active fire products from NASA firms. You can see there are some overestimations. I'm not sure some of you have seen in the social media. It was trending August last year. If you zoom out to see the whole continent of Africa and South America, in the social media, people say, hey, big media, there are many cities in Africa and South America that, close fires. It was not reported. Only, the Western cities are reported dominating the media. And this was trending again Actually, in January during the wildfires, I was interviewed by the Swedish TV. They have viewers asking the same questions. Actually, partly is due to the overestimation. If you look at Africa, South America, there 1/3 of the continent look like hot spot. It's burning. But if you actually zoom in, it's partly due to visualization, partly due to overestimation. So therefore, there's a need for improved detection to detect the active fires more reliably. So yeah, so we also have this medium resolution model spheres. You can see the trend of progression, but it's kind of difficult to track in a detailed level, but it's good to use for situation awareness. So then we have higher resolution data, mid-resolution data for burn area mapping. If you can map burn areas, then you can track the progression in near real time. In this class, I mean, of course, we can also use models and VIIRS. VIIRS has now monthly burn area products, and VIIRS usually it's accumulated active fire points, and then you can accumulate active fire points. But for mid-resolution, every few days, we have here Sentinel-2, Landsat, and you use shortwave infrared, near infrared, and you get the difference called DNBR. But then on the other side, you can also use daily, sub-daily mapping, use MODIS and VIIRS and Sentinel-3, for example. And on the radar side, we also have C-band, L-band SAR, Sentinel-1, for example, and ALOS Pulsar, and the Canadian RadarSat Constellations mission, compact pulsar. So we will touch upon all of these briefly, not detailed. So these are just comparison of, from twice daily to every few days. Then, you have an image. I just want to say the usefulness of radar. Of course, the Landsat Sentinel burn areas are easily detectable, but unfortunately, you have a lot of clouds in boreal environment, Canada, Sweden. And also on the right-hand side, you actually see a California fire. I actually thought, California was sunny. I didn't realize they also have quite many cloudy days. So, here is an example. You have nighttime, you have 50% cloudy, then you don't have a lot of detections. So SAR can play a very important role. So here I just put optical data and SAR data together, and then you can really achieve near real time using higher resolution data set. So just some examples of the Greek island fire, detected by Sentinel-2 and also Planet on a daily basis. Then we also have Sentinel-3 on a daily basis. So you can have variety of optical sensor, no problem in sunny Mediterranean environment. But when you move to north, the Canadian wildfires, you can see that, this is overview using VIIRS, a lot of clouds constantly covering the burn areas. Then with radar, we're able to track the progression of this large fire called Dunny Creek Fire. And here is the burned area seen on Sentinel-2. In terms of products, monthly MODIS burn area is quite a good reliability, but you can't really track it in near real time. It's a monthly basis. So what's going on in terms of active fire detection? I already mentioned all this satellite data, and people also use Sentinel-2 and the Landsat, not only the low resolution ones. When possible, there is high resolution data. You can also detect active fires using shortwave infrared. So then for burn area mapping, we have, the 100-meter, hundreds meter of resolution daily. You can do daily progression, sub-daily progression. Landsat Sentinel-2. You can also do every few days. Then you have Sentinel-1 and ALOS Pulsar. Hopefully soon NISAR will be available. So we have variety of data set. And RCM, the ambition was to have daily coverage for Canada. I'll show you some examples. Then often this active fire detection using multi-criteria threshold, that's part of the problem why we have, overestimation or, issues because you have to find the right threshold maybe for different regions, different climate zones. And there's a spatial deep learning approach and temporal deep learning approach, and of course, spatial temporal deep learning. So there are a variety of methods can be used. There are research gaps and challenges. First is really the accuracy and frequency of the current active fire burned area products need to be improved. And we also have spatial temporal different deep learning models are not well explored for wildfire detection. And we also have lack of comparative studies on C-band, L-band, SAR for burned area mapping, and also RCM compact pole. Is that different than dual polarization data set? So there some research need to be done. I think most of you maybe already knew about this. So you have, let me see. Yeah, so burned area, unburned area optical data is quite easy to detect. But for SAR, it's a little bit difficult. It's not as easy. So you can see the big difference in terms of SARs, VV or VH. So COPOL seems to perform better than on a cross-pod than COPOL. So, but this is not always the case, also depending on different conditions, environmental conditions. So we have conducted field work and we combined information with meteorological information and try to better understand backscatter interactions with the burned areas and burn severity. So yeah, just want to say that for active fire detection, we use GOES and VIIRS as the examples I'm showing today. And for near real-time burn area mapping, use VIIRS, Sentinel-1, Sentinel-2, Pulsar, and RCM. And their time series analysis as well by temporal analysis. So let's go into directly active fire detection. So in terms of goals, geostationary already mentioned, high temporal resolution, low spatial resolution. Definitely you can see active fires collect closely. So yeah, so here are the indicators we use difference of different bands and then get the difference. Then we can detect the burned areas. But here we used study areas in 4 different largest wildfires in California. We use those hotspots to train the deep learning model, and then we deploy it in several sites in North America and South America, many more sites than the training areas. So let's see how the methodology. We use the deep GRU network for early detection of active fires. We compared with the GOES official products to see, are we detecting those earlier than, reported time or, later? And also, are we detecting it more reliably? So this, if you're interested, I don't have time to really go through the details of the methodology. So check out the paper published in 2022. So here you can see that earlier than officially reported time, if you the GOES image, it's 36 kilometers above Earth. So for continental US, it's quite good. But for like north in Canada, it has a huge distortions. It's more difficult to detect those active fires due to distortion and also data quality. But anyway, the high latitude, we still detect some earlier. And majority of mid altitude is quite good and low altitude is okay. And then similar time frame, and then later, partly due to the distortions. So majority we can detect earlier and also more reliably than the products, existing products. So here just some qualitative result as well. You can use this to track. This is the overlapping on the Sentinel-2 image, higher resolution, and you can see the progression of the hotspot or where the fire fronts are. Okay, then we're moving to the next, we move into higher resolution from 2 kilometers, we could get down to 375 meters resolution. But this is sub-daily, we have day and night imagery. And then, if you have active fire and non-fire, then there's a big difference. So we use the VIIR's daytime imagery. Mainly, we haven't really done it at night. We will deploy that to night imagery by training on the night imagery dataset. So here we have 18 wildfires in North America from 2020 as training site, and test site we have US, Canada, Sweden, and Australia. So we try to see what's the capability with our deep learning models. So we done some pre-processing and of the data. Then we developed this transformer for active fire detection model. And so this is a tokenized time series using transformer network, a spatial model, temporal model, sorry, for active fire detection. So we use a time series of images to improve the detection of active fires. So these are the results. We compare with VIIR's active fire products and also accumulated. So if you're interested, this paper is published in IEEE Transaction on geoscience remote sensing. We also have another active fire detection paper on Sentinel-2 for active fire detection. If you're interested, you can also look at that, but I don't have time to mention that here today. So in terms of qualitative result, we compared with GRU, the earlier model we used for on-goes and long shot an LSTM model that we can see that IOU and F1 score, we have achieved higher than the other models. Again, we also compare with some spatial models, not only temporal models. So these are achieving the best result. You can also see the temporal model seems to perform better than the spatial models. So here you can see the progression detected on the daytime imagery. And then how do we achieve near real-time daily burnt area mapping using VIIRS and auto-regressive swing transformer? That's the next I would like to show. So as all you know that often people use accumulated active fire points as burned areas, but satellite only captured on the instant. So there are active fires during the capture time. You don't really get it when you accumulate it. So for progression, you really need to map the burned area. So then we decided to use VIIRS to try to map daily burned areas. So this is a recently published paper in International Applied Earth Observation and Geoinformation, and we have utilized again the daytime imagery for burned area mapping. Unfortunately, nighttime you only see active fires. It's difficult to see burned areas. So we have used 3 years of training and validation data set in the United States from 2017 to 2020. Then we compared with the accumulated active fire, accumulated hotspots. Then we have test sites, large Canadian wildfire events in 2023. As test areas, just to test our models, capability. So here we used a special temporal model. It's called a swing transformer, autoregressive. We have an autoregressive mask applied to the swing transformer for this. So it's a special temporal model. So what are the results? Let's see. So in terms of comparison with spatial models and spatial temporal models, so our model achieved the highest accuracy. Without the autoregressive, it's also quite good result. And on UNET, not bad either, UNET 3D. Also, I would say all of these are quite good spatial temporal model. Then only the spatial model, then the swing UNET 2D is actually quite good. And LinkNet, not bad either, but I think 0.85 is still much better than 0.80. So we also look at the baseline cumulative years hotspot by looking at, quite many large fires in Canada. So some fires are, about 500,000 hectares burned. So we are really comparing huge areas. So you can still see that in terms of, our result and the accumulated result. So on average, it's still good, but the performance vary from fire to fire. In general, our method are definitely better than the accumulated active fire spot. Yeah, just to compare, so you can see we have less false alarms than the accumulated result. Now we're moving to radar. So how do we use SAR for burned area mapping? So for some of you who have not used SAR, just to show SAR have different wavelengths, X-band short wavelengths to P-band much longer wavelengths, how a Austrian pine is saying on these different bands. And also SAR has 4 different polarizations and how SAR interact with different terrain features. You can see it here. So I will not maybe say more. So here we actually created initially a 3-year data set, 2017 to 2019, all Canadian fires we collected data for C-band, L-band SAR, and we, as you can see, we look at, we use the training set and covering variety of land cover types, mostly close forest, evergreen needle leaves, and there are other type of fire, forest and land cover types as well. And we also split to test training and testing sets as well. But recently, we actually extended this data set to 2023. So these are, many wildfires in the past 7 years. And also in United States as well, we collected for both Canada and United States. First we did investigation using Sentinel-1 SAR because it's every 6 days in Europe and outside Europe every 12 days. So we can really try to check the capabilities. And about Pulsar, unfortunately, we don't have access to many images. We actually just have this annual image that was uploaded to Earth Engine. We try to match the closest acquisition data of Sentinel-1 with Pulsar in order to do a fair comparison. So this is an example of a Swedish fire 2018. We have Sentinel-1 and Pulsar-2. Look at the burn areas. Seems like Sentinel-1, what we've seen is like low severity areas we have difficulty detecting. I think seems like Pulsar was able to capture the burned area better than Sentinel-1. And also SAR is not that easy. So after burn, depending on the, if it rain or not rain and how quickly you collect the image, sometimes you have definitely backscatter decrease, but sometimes you have backscatter increase due to precipitation. And sometimes for different land cover, for example, grass fire, before the fire, when it's already dry, and the radar penetrates through the grass, and then after burn, maybe there's not much difference at all. So it's rather complex here, just to show some examples, how you see the burn areas on Sentinel-1 and SAR data in some of our study areas. So we have developed a different type of models for using SAR as well as actually Sentinel-2 for burned area mapping. So on the left, we have used the UNet model, and on the right-hand side, we use the total variance regularized neural networks. So here we implemented like progression-wise learning without forgetting, and compared with on-the-fly training as well. So we have a number of different publications using SAR for burned area mapping or near real-time proven, examining the potential. So if we have daily SAR images, it's possible to use SAR for near real-time wildfire monitoring. And as you can also saw that in the images I showed, SAR is very difficult to interpret. So we have also attempted using GAN-based SAR to optical translation for wildfire monitoring to make it easier to interpret. So make it look like Sentinel-2 type of data, and then try to detect burned areas. So if you're interested, take a look at our publications. So here, just to see was the fire in Dunny Creek, 2023, wildfire in Canada, 500,000 hectares burned in this area. We also have tested in many different fires. We were able to track the progression and compare them with Sentinel-2 acquisitions, and the results are quite accurate. And then that was in Canada. Then we had the transfer to United States. Dixie Fire, it's also a good result. And this is Australia, a large fire, 1 million hectare burn near Sydney, 2019. And then we also transferred to the Fraser Island fire. It's a UNESCO heritage site. We were able to detect burn areas really well. Then in terms of comparison of Sentinel-1, Sentinel-2, we also try to match some sites. We don't have a whole lot of data because I would like to have the area burned as soon as possible, because after a year or two, actually it was easier to detect than immediately after, because usually after the precipitation and also clearing of the areas, then it became clear cut, it's easier to detect. So we try to get it immediately after burn to have the pre and post pairs, and try to compare the C and L band SAR in terms of different severities. Yeah, this paper is currently actually under revision. So just to show some preliminary result, L band using attention unit achieved the best result. So it's quite good result. Yeah, so we deploy it in several study areas, and it seems to do quite well. And here are just some qualitative results in terms of, we have highlighted the different burn severities and try to show the performance. And also, low severity are harder to detect. So seems like Sentinel-1 in compared to Pulsar perform slightly better. Just finally, quickly, talk about radar site constellation mission for burn area mapping. Radar site constellation mission are 3 satellites mission that aim to cover Canada, on a daily basis. But there are many different requests, so you have to request data through different agencies. So when we try to get fire data, actually we don't have daily. And also there are so many different beam modes, it's difficult actually to match the pre and post with the same beam modes. If you mix SAR in different, angle and beam modes, and it's difficult to actually detect fire, especially in mountainous areas. So we got a lot of data, but trying to get the right pairs has been quite challenging. So we have requested CSA to, try to collect data in the constant beam mode. I think actually ESA made the right decision for Sentinel-1 from that perspective, instead of have many beam modes. So you can actually see, the burn areas were, highlighted quite well on RCM. This is compact POL data. We use the polarimetric decomposition. We selected quite a few fires from 2023 and 2024. Yeah, so we need a bunch of pre-processing. I skipped that. And then we have this swing unit, similar methodology as L band and C band SAR. And we actually use, we compare the number of decompositions. We selected these two seems to perform quite well as, test. And let's see what are the results. Yeah, we submitted this paper. Also now got a major revision, just came back. So it's a very new result. So yeah, we have sites in BC, Quebec, Northwest Territories, all in Canada. We don't have data outside Canada for now. Yeah, I would say this combination of log ratio and polarimetric decomposition perform better, provide the best result. I think, yeah, F1 score is quite good. IOU, it's not as good because we compare with, this high resolution Sentinel-2 hand-drawn polygons. So maybe the low severity burn areas didn't get detected. So yeah, so here are some visualization of the result and also the decompositions, this log ratio, then the decompositions, and these are the unit output. Yeah, you can see the challenges we have is we have some patches here, some patches there. They're not very consistent. So anyhow, just want to have a final comparison. You have Sentinel-2 and also the official fire polygons highlighted here. There are a lot of holes, unburned areas. If you use low resolution models and virs, obviously you don't get the details. And we use Sentinel-1 SAR, we actually managed to get a lot of details. We also have progression over time that you can detect this how a fire progresses. I will stop here. So thanks very much for listening. Any questions?
Yes, thanks a lot, Yifang, for this very great and nice overview of what you can do, especially with the satellite data that we have, but also with the methods. I hope I think there's probably quite a lot of questions concerning this great overview and also results that you obtained. I would try now to read some of the questions. I saw only in the moment one, but please, everybody who likes to pose a question, please put it into the chat.
There's someone raised the hand.
Yes.
Puma.
Okay. I think this person can already open up now. If not, then I can do this. Let's see. I can't really. Oh, yeah. Wait.
Is he allowed to? Oh, there's another hand, Ahmed Omar.
Yes, I have already opened for both, but they are not responding.
Okay. Hello. The two of you who raise your hands. Can you ask your questions?
Yes, can you hear me?
Yes.
Yes.
Okay. I want to ask about the useless result.
Sorry, I think the connection is very bad.
Eco-stress for mapping wildfires.
Sorry, we didn't hear the whole question. Can you please repeat?
Yes, I want to ask about if you try to use eco-stress during the wildfires.
Some important words were missing.
I think there was a question already of this person before in the chat, and it was asking, what about eco-stress data? He attended a conference before, and he's asking if this can be also used for forest fire mapping.
Sorry, I'm not actually familiar with that data set. Irina, can you tell me what it is?
No, eco-stress, I also don't know. I don't know these data sets, sorry.
No, not. Can you provide some information what type of data it is?
Yes, I will share a link on the chat to tell more details about it.
Okay, thank you. So
Thank
then,
you. But I think we have quite a lot of question in the question and answering section, and I will start to read them now. This question is from Anirban Roy. Are the detection model having input from both modalities together or one modality at a time?
we have models that can handle both modalities, but usually we do one at a time. The reason is we want it near real time. So then often they're not acquiring on the same date. So if they're acquired on the same date, we use both modality. If it's only one modality available, we only use one modality. Good question. Now we see that eco-stress provides 70-meter land surface temperature and emissivity data. So yeah, if you have land surface temperature data, definitely that can be used for wildfire monitoring.
Okay, great. So then there's the next question from Aprilia Nidia Rinasti. In the GOER-RB data, spotted that the study can provide according to the distinctive channel B7 and B14. Do you think it can be improved in tokenizing, instead focusing only on the temporal and the spatial resolution?
I think definitely there's a potential to improve. There are attempts, at least from our side, and try to see how do we downscale, 2-kilometer data, maybe using VIIRS or MODIS. But it's quite challenging because of the resolution gap and also the locational accuracy. So I think it's possible to do more to improve. Then you would have, every 15 minutes at, 375-meter resolution for sure.
Okay, thanks a lot. There's another question from Georgios Giannopoulos. Could you discuss a bit the distribution of the test data set? It is rather important to be able to evaluate the generalization of the presented metrics to real-world scenarios. It is often the case that the more or less balanced test data set between fire and non-fire instances is used, while the real-world distribution is extremely imbalanced toward no fire.
Yes, I think that's an excellent question. Definitely, this is very important. What we have been doing is trying to, split in the, let's say we have 7 years of Canada, United States. We split maybe 70% for training, 20% for testing, and 10% validation. We also go out of the region. We go to Australia, Europe, and other regions, South America. Then we do the testing not only in the the areas that the model have seen. Then we also go out to the unseen areas. So we try to be very thorough in terms of testing. And I agree with you, like real world unburned areas are, large than burned areas. But what we're trying to do is we don't really scan through the whole globe looking for fire. We only look at where is the active fire spot. We focus in that area. So in that sense, you don't really have a significant unbalance.
Yeah, thanks for answering this question. Then the next one is from Javier Quispe Varillas. What methodology do you recommend for Andean areas of Peru with a high percentage of clouds?
Yeah, when you have clouds, definitely, I would say, first of all, use multi-sensor. That's my approach, whatever that's available. We have seen sometimes, VIIRS and MODIS have a couple hours of precision difference. That actually, sometimes clouds moves. Then, it's covered by MODIS, but it was available in VIIRS. So you can use all data. And of course, you should try also to use radar. If nothing available, use radar. But unfortunately, right now, we don't have daily radar. So my recommendations to acquire all data to see, what you can do. Even there are some clouds you can, or smoke, you can actually see in some gaps, you see active fires.
Yeah, thanks. I think this makes really sense to use all what is possible. I agree. And then there's another question from Adnan Siddiq. Given that some agencies are already providing fire detection products, do you still think there is a need for further research?
Sorry, Irina, who is providing the fire products?
So agencies, I think in general, there are some agencies which are providing fire products.
Yeah, NASA firms and European, Copernicus. It's the same as firms. We have shown, that's why in the beginning I showed you the products from firms. The active fire products, there's some overestimation. quite a significant overestimation, and because all kind of hot objects being detected due to the use threshold-based approach, and clouds and some other issues. So that's why that was a motivation for us to do deep learning-based approach, and also time series that using spatial temporal model time series data to improve the result. It's because the reliability of the products provided by agency burn areas is a monthly product. It's not helpful for near real time monitoring. So that's the key motivation why we're doing what we're doing.
Yeah, great. Thanks for this. This makes sense. And then there's another question from Ankit Kivasara. Can you please explain without temporal data how to detect wildfire?
Can you
Oh,
repeat?
sorry.
I
Yeah,
get it.
it's a little bit strange because it's written wildlife, but I assume it's wildfire. He's asking, when you do not have temporal data, but you have only one instant acquisition potentially, how you can detect wildfire.
Oh, yeah. So let's say active fire, if you have this time series, we have a number of days, acquisition, because sometimes you do have clouds, right? So this, by using the time series, the previous days that help you to detect, reinforce today detection. So that's why I think time series are important. We have shown that you use the temporal model outperform just a spatial model using one date.
Okay, thanks. And the next question is from Haniel Datka. Thank you for the presentation. How can we explain the holes inside the BA map? Is it possible so sorry, there's the next question. Is it possible to have some parts unburned in the middle of BA part?
Yeah, that was an excellent question. So you can see here on the green one, the holes are unburned. So if you have coarse resolution, unburned become burned. So you have statistical burned areas are much larger than real burned areas. Often, like very young forests, I've been to the field, they are actually unburned. So there are quite many patches of unburned area in the burned area. Fire moves very fast and they jump. And so often you have those. So therefore, a better improved burn area mapping is very important. So yeah, the holes are mainly due to unburned areas.
He has a second question, the same person. What would be your suggestion about data for detecting smaller fires, for example, in this area?
Oh yeah, then I would say definitely go with higher resolution. I mean, let's say if it's not cloudy, you can use the planet there daily, but unfortunately, we can only get a small data set for testing. You can't really use it as an operational thing, and also could due to cloud cover, and you don't really have data. So there are challenges. So we are working with daily high resolution monitoring now. So maybe I can share in the future. The paper just got submitted. We haven't heard back, so I'm not presenting that right now. But we are working on hybrid between, high resolution and low resolution. How do we improve to have daily high resolution monitoring?
Okay, the next question is from an anonymous person. He's asking, how can GAN be used for detecting wildfire? I assume that's
the GAN-based model
yes.
is used for translating SAR data to optical-like images. The reason was SAR was harder to interpret, to try to convince the users like Wildfire services to use it, to say, oh, they are used to optical data. They've used Landsat and the MODIS vias. So then we translated the SAR to optical-like images, and you can use this DMBR, the burned normalize burned area ratio, then you can detect burned area easily than just detecting from SAR. They're hesitant of using it. So we have tried that, and it seems to be working. We also use the diffusion models, a newer model, and also translate SAR to optical. That seems to work quite well. And if you're interested, you can also check out our Argus paper from last year on that.
Yeah, thanks a lot. The next person is Rishi Ganesh, and he's asking about the significance of using daily temporal data for wildfire observation. Is it only because the wind speed and direction are dynamic in nature? In principle, the
Well, when
importance
you
why
have
we need temporal data.
Yeah, I think when you have a wildfire, I talk to firefighters. Of course, they want every hour, every 3 hours, and the worst every 6 hours. So they want as much as possible to, for if they need to issue evacuation orders and, protect critical infrastructure, property, human lives, or really to deploy resources. If you have in Canada, for example, thousands of fires are burning, or hundreds, and you have only limited resources, similar with Los Angeles fire, and you only have some helicopters, and water is limited. Where do you put your resources? Of course, the sooner you know where is the active fire front, which way is progressing, it's really, really important. I would say sub-daily, definitely daily is important. For fast moving fire like the Los Angeles fire, you need sub-daily monitoring.
There is the next question from Anirban Roy. The data used for the training models, is it pre-processed data?
Yes, you need, let's say what we get, for example, it's a lot of work to collect data. So we have the fire polygons from those wildfire services, and we get them from, different sources. Then we have to sort of harmonize them and to make sure they're all correct. Then we match the Sentinel-1, Sentinel-2, VIIRS, models, all this data. We collect images pre-fire, post-fire. Sometimes we also collect during fire. So it is quite a lot of work. We have worked on this, several PhD students and research assistants working on this for quite a long time to create this data set. So then we can use for training and also deployment.
Yeah, thanks a lot. Then Adnan Siddiq has next question. Does reducing channels in case of deep learning with SAR images help improve accuracy of detection?
Reducing channels means you only use, let's say mostly it's really to reduce the computation. We know that maybe shortwave infrared, near infrared, and red, for example, they're good for burn area mapping. Then we don't need all the other bands, so we just select those. And since we have thousands of fires, when the fires are big, 0.5 millihectare, if you make them into patches, they're like millions of patches. So it's a lot of work. I think it's also important to reduce, but you can also use all channels. We have tested on a smaller data set. We show that, a few bands are good enough, representative for all the channels. For example, Sentinel-2, you have 12 bands. You don't need all of that.
So you probably there's importance, right? Which one is let me say more important, which one not?
Yeah, we do relevance testing. I mean, of course, you can also use principal component analysis, but then that has most information content, but may not representing burned areas. So we knew for burned area mapping, shortwave infrared is really important. So that definitely need to be selected.
Okay, there's another question from Supriya Limbo. How do you register the images, optical and SAR?
Pardon, can you repeat?
Yeah, the question is how you can register geocoded or geocoding the optical with the SAR data because they are so different. Because the one is side looking, the other one is more.
Thank you. But fortunately, for example, Sentinel-1, Sentinel-2 are perfectly registered, thanks to the space agency. And also the LS pulsar data we got are already uploaded to Google Earth Engine. It's an analysis-ready data set. We didn't have to do registration, but for VIIR's near real-time data and GOES near real-time data, we actually have to do pre-processing geocoding ourselves. And it's quite an effort, but we created a workflow that we can do this automatically. So from grabbing the images to to input that into deep learning model, it's automatic. Actually, I wanted to say Canadian radar set, we actually have to run SNAP. Also, we wrote codes. We can process them in batches, and then we were able to line them with Sentinel-1 because we want to compare dual polarization versus compact pol.
Yeah, thanks a lot. There's another question from Anil Banroy. Just wanted to understand about the near real-time aspect of the study. How is the near real-time aspect addressed if the data is downloaded at the ground station first, pre-processed, and then provided for the detection model to consume? I saw in your slide that the LEO satellites are doing a couple of passes in a day. How would they provide near real-time insight then?
Yeah, good question. So from a satellite provider perspective, let's say VIIR's dataset, we download near real-time directly from NASA, USGS. So basically, they actually take a few hours. So from a space agency perspective, the near real-time is around 3 hours. So they have to process the data, then they release the data, then we grab it. As soon as it's available, then we run our workflow. Since our model is already trained on existing data like past fires, we can deploy it quickly on the new data coming in. Then within minutes, we're able to get a detection. So then it's after the space agency's a few hours delay, we can do it pretty quickly.
Mm-hmm. And you're posting this information then somewhere, or you're providing this information to agencies?
We have an app. Yeah, we have an app, Wildfire app. We have given to some users, interested users, to test it. So we can track. Actually, maybe I have a next slide. We can track in Canada, United States, and EU on the like a whole continental scale. And we also have layers of human settlement, critical infrastructure, so that you can actually see which way the fire progresses, and so that they can, better prepare themselves.
Yeah, very great. There's next question from Wubertu Bilay. He's asking, how do you validate the model you have developed?
Yeah, we have, we split the data, our labels into training, validation, testing, and then we also have a validation set outside the region as well, try to see the transferability. So we try to do very thorough, independent validation. And also, if let's say the student who developed model, we don't use him to do this validation, we use another student just to be independent, so that you don't get biased, where it's performing well, you only get result from that area.
Great, thank you. The next question, Nabayu Otidas. Can we assume that performing data fusion from multiple sensors would always be helpful for predicting wildfire? And the next question, what does the experimental results reveal?
Yes, we had we have been focused on independent sensors, but for one instance that, one study we use, because Sentinel-1, we use on-the-fly training, so we use very cost labels because it's a new fire. The Wildfire Agency hasn't got any training. At the time we started in 2017, there hasn't been a lot of data set. So we actually use very cost labels, but we try to use Sentinel-2 whenever it's available to have more precise training. Then we use SAR for, detection. So it's definitely, if you say combine CNL band, dual polarization, it can improve the result. But the main challenge is it's difficult to get Sentinel-1, Sentinel-2, NISAR or ALOS pulsar on the same day. It's extremely difficult because we try to use Sentinel-2 during fire to validate our SAR-based result. We only get a few that they collect exactly on the same day. But it's tough.
Yeah, thanks a lot. There's again an anonymous participant which have a question, and he's asking, or she, are the models open source? Can you share any links?
I think some of the models are open source, some are not. I think our earlier publications, I don't think we have shared models, but I think some data set we have also open. I think in the IEEE portal, we actually have published our 3-year data set from 2017 to 2019. So if you want to, I can't remember it's US or Canada. So anyway, so there are some data set we have opened up already, but right now, because our PhD students have spent so much time collecting the data, they need the data for their thesis. So then some of the, data or the models are not open, partly because they want to have their papers published.
Yeah, I would say that's a good reason. Okay, then the next question from Mohammed Sikis SBT. What is your recommendation for using the same approach to other forest disturbance, such as selective logging or insect defoliation?
Yeah, that's a very good question. I would say for clear cuts, it's change. So for burn area, we also detect change, right? So it's sort of a change detection problem that I think you can adapt. But I would say maybe fire and clear cuts are slightly different. So then you actually have to collect maybe training. We haven't really tested on clear cuts. I wondered probably it would work. If it worked on fire, it should work on clear cuts. It's easier. But for the insect infestation, it's more challenging, depending on the stage. I would say it's the buck beetle attack we have been looking at. The very early stage, the green stage, I think it's very difficult to detect with SAR. We actually, or even other optical data, because it doesn't show much difference. Maybe hyperspectral helps. But when it's at the late stage, I think, or mid stage anyway, that it's possible also to detect. Basically, the forest has changed.
Okay, there's again a question from Anir Banroy. This kind is also, could you kindly highlight the modalities used for modality fusion in this study? Is it spatial and temporal? And thanks for the great presentation.
Oh, thank you. Yeah, good question. So I had a summary slide about the spatial and temporal. So we have multiple, spatial resolutions, and also time series data from every 15 minutes to daily to every few days. So it's a great range of data we have looked at. So in terms of modalities, basically you have thermal, you have shortwave infrared, near infrared, multispectral. Then you have also SAR, and SAR you have different bands, and also dual polarization versus compact polarimetric. So there are a variety of modalities.
Okay, there's also again another question from Mohammed Sheikh SBT. Is it true that temporal resolution have more priority than the spatial resolution when we talk about near real-time study?
I would say both are important because, goes every 15 minutes, but it's not widely used, partly because it doesn't detect very small fires. That's why you see the firms on NASA and the EU products, the wildfire information systems, that it's mostly multi-severes. So they have, twice daily reasonable resolution. I think that kind of data have been used by firefighting agencies. Of course, the higher temporal and spatial resolution they all want. I hope the next generation satellites can provide that.
Yeah, great. Yeah, thanks. Then the next question is from Vubetu Belai. I appreciate your awesome presentation. What type of noise removal method did you use? That's the first question. And the second is, what machine learning technology is more accurate?
Okay, good question. Yeah, I mean, noise removal are mostly used for SAR. We actually use the log ratio and also we have on top of log ratio, we have used the time series to temporal mean to further regularize this to reduce more noisy data in order to make it a little bit more representative or what do you call it? Normalization. So we call it like a K-map. So a log ratio and then time series of 2 months pre-fire and to regularize this. Now I don't remember the second question.
The second was, which machine learning technology is more accurate?
I would say, depending on what you're looking at for burn area mapping, we highly recommend the spatial temporal model.
Okay, then there's still some question about from Bayu Satya Atitama, sorry. He's asking, or she's asking, currently my team under the project to model the fuel loads and the fire probability in Indonesia. I hope it is appropriate, but is it possible for us to consult or chat with you regarding our research? Probably yes, right?
Yes, definitely. Yeah, be happy to also add study areas in Indonesia. Yeah, definitely.
And there's another question from Javier Quispe Varilas. He's saying, to be able to consult more technical topics, where can we contact you to transfer your learning to our country?
You can reach out to me with my email. I don't know if it's published somewhere. It's otherwise my first name at kth.se. I can type it in the chat. So anyone want to contact me, use this email.
I think you had your email address in the beginning of the presentation. So
yeah, and also now it's in chat.
When it's and when it's in YouTube, you can also have a look on it. Okay, and then the last question I have here from Adolfo Perez Duran. Excellent presentation. Thank you. Based on your experience, how will access to curated and processed training data sets affect your research?
Well, deep learning is data greedy, so it's really important to start with creating good data sets. Some people train on one fire, deploy on another fire, it will not work other fires. So it's really important to create large data set, and we are actually, we have another data set are forthcoming, 2 other data sets. We will try to open it up for the community to use and test. I also would like to say, maybe you have heard, I didn't present that work. It's called geospatial foundation models. There are many different geospatial foundation models. We have created a benchmark, global, benchmarking of different foundation models using open dataset that include a FIRE dataset. That's not from us, but we will upload our dataset as well. Then you can actually try out the foundation models that are implemented, and you can even upload your own local dataset to see how they perform in your areas. So definitely having a good dataset, very, very important.
Okay, I'm just checking now some question in the chat still, which are not at the Q&A, but the other ones. Here, for example, is one from Wahiba Dardouri. Can we compute land surface temperature using data sets only from Sentinel-2?
No, because Sentinel-2 doesn't have the thermal bands. So you need Sentinel-3 or VIIRS models.
Okay.
No Sentinel-2, unfortunately.
Okay, there's another question. Thank you for the insightful talk. Can you provide an estimate on the quantity of image data you need for training, validating, and testing the DL model?
I think depending on what you want to do, let's say if you are really interested in only a region or local areas, maybe you don't need a huge amount of training testing data. But for us, we want to have developed globally applicable methods. Then we need really large areas, training data representing different local climate zones, different ecoregions, and also different terrain conditions, different type of fires, forest grass fire, land cover types. So then you need a huge amount of data sets. It really depends on the purpose.
I think probably most of the things we have already now asked. I think there's many more questions, but I think we need now slowly to close it. We are quite over the time. I would like to thank you very much, Yifang Ban, for this really excellent presentation. It was very insightful, very informative. It gives a really huge perspective of what you can do using remote sensing with multiple sensors, which is not only focused on optics or SAR, but it's a combination. So it was giving really a great view on this, what remote sensing can do, and then combining this with AI techniques, which are up to date. So thanks a lot. And and I wish all the participants, I would like also to thank you for your very active participation, asking so many questions. And I hope to see you again back to the next webinar that we'll have at GRSS. Thanks a lot and have a good day, a good morning, or a good evening. Goodbye.
Thank you. Bye-bye.